Hi, this is Mrs. Rutchling. Welcome to Chapter 6, where we will start to look at the composition of the chemicals we've been working with. The FDA gives us guidelines for how much sodium, but the mass of the sodium that we eat is not the same as the mass of sodium chloride, which is where most of our sodium comes from. Then we have to look at, well, how much sodium chloride, how many grams can we consume? And we know that its formula is NaCl, and so there's one sodium ion for every chloride ion. Since the masses are different, we really can't tell the relationship from the chemical formula alone. Sometimes you will see things that are sold by the pound, which is easier than counting them out. And that's similar to how many atoms are in this mass. With atoms, we have to use their mass because we cannot count them individually. There are far too many to count. You could count them the rest of your life and barely get to the number of atoms that are in a single grain of sand. It takes a lot of atoms if we're going to measure it in the lab. If we want the mass on the periodic table, which we've been looking at for individual atoms, AMUs, if we want it to be masses in grams, it would be 6.02 times 10 to the 23rd. This is called Avogadro's number, and the amount, or this unit, is called a mole. Has to be lowercase, and sometimes you will abbreviate it MOL, dropping the E. And a mole is just a number, so we know a dozen is 12. If you've ever seen something in a gross, it's 144. A ream of paper is 500 sheets, and now we have a mole that is 6.02 times 10 to the 23rd. It's called Avogadro's number in honor of Amedeo Avogadro, who studied quantities of gases, and he found out that no matter what gas you have the same number of molecules present. And we'll look at that when we get to our gases chapter. Particles is a general word, and it can represent atoms, molecules, formula units, or ions. So if I have a mole of carbon atoms, that means I have 6.02 times 10 to the 23 of the individual atoms. I could not sit here and pull off a mole of atoms. It would take the rest of my life, but this gives you an idea that I'm talking about the individual atoms. I could talk about a mole of water molecules, and then I'm talking about 6.02 times 10 to the 23rd of those individual molecules. If I had an ionic compound, instead of molecule, I would call it a formula unit. And then I can have ions, and remember that if I have a mole of ions, each one of them would carry the charge of the ion. If I have a dozen of cookies, a dozen of cars, and a dozen of aluminum atoms, you can see that those masses would be very different. The cookies would be much less than the cars, but the smallest would be these 12 atoms. We have the same with moles. If I have a mole of cookies, compare that to a mole of cars, compared to a mole of aluminum atoms. I have the same number, but the mass is going to be very different. If I was looking at how large a mole is, Avogadro's number, here are some examples. If I had unpopped popcorn kernels and spread them across the U.S., the country would be covered in popcorn to 9 miles. And if I had a mole of pennies, if I distributed them to everyone in the world so that they could spend $1 million every hour, every day for the rest of their lives, I would barely use a mole of pennies. So where did Avogadro's number come from? It was measured, and initially it was measured using the Millikan oil drop experiment. And so Millikan took the spray bottle of atoms, put them out here. They were drawn into this viewing chamber, which was electrified, and then you could look through the microscope. Of course, now we can use X-ray technology to see those atoms. We're going to use Avogadro's number as a conversion factor. I've written it in a very general form. So I have 6.02 times 10 to the 23rd particles over 1 mole, or 1 mole over 6.02 times 10 to the 23rd particles. When I use this, I'm going to substitute something in for particles. Could be atom, an ion, or a molecule. Let's give this learning check a try. We have a given 0.500 moles of aluminum, and we want to know how many atoms. I do suggest that you include the zeros here because those are significant and they will help you figure out how many significant figures your answer has. We need to use one of these two, and because I have moles here, I'm going to want moles on the bottom. So notice in my conversion factor, I'm using atoms and moles because I've started with moles and I want atoms. So I've customized it. Instead of particles, I put what I have. I can cancel out my units and I end up with atoms of aluminum. I end up with 3.01 times 10 to the 23rd atoms of aluminum. And notice that I have both of those on there, and your proper answer should include both. Pause the video and give this one a try. Start with atom and go to moles. When I set my problem up, I put atoms of sulfur on the bottom. Notice that the number always goes with atoms, molecules with the particles, and then the 1 mole is of sulfur, and I end up with 2.99. I only have 2 significant figures, and so my answer is B. Pause the video and give these 2 problems a try. I start off with my given, and since I have atoms, I need to set up my conversion factor. The atoms is on the bottom so they can cancel out, and I end up with moles. I have 32.6 moles of strontium, and I want to know how many atoms, so I set up my problem. I want to make sure that I have it set up so I can cancel, and then Avogadro's number is with the number of particles, and I end up with 1.96 times 10 to the 25th atoms strontium. Pause the video. This time we're going to use molecules, but the problem is set up the same. You should have started with 4.99 moles of methane. I want to set up my conversion factor so that's moles is on the bottom. And this time I substitute molecules in for particles. I end up with 3.00 times 10 to the 24 molecules of methane. Notice I have 3 significant figures, and so my answer should have 3 significant figures. Let's try the real world application. Pause the video once I explain it. We have a minimum amount that the FDA says we should have 1.3 times 10 to the 18th atoms in 1 milliliter of blood. And the lab reports that the patient has 3.0 times 10 to the negative 5th moles. And so we need to convert so we can compare. I converted the patient's value to atoms to compare. Of course, you could do it the other way, but I chose to do moles to atoms. Pause the video and give this one a try. I start off with my moles and I convert it to atoms. And I find out that there are 1.8 times 10 to the 19th atoms calcium. That is higher than the minimum amount, so this patient is not at risk for osteoporosis.